Welcome to solverfy.
Question number 58 includes two problems of a weak acid being titrated with a strong base. For the first weak acid, it's monoprotic, and there's only one equivalence point. But for the second weak acid, it's diprotic, and there are two equivalence points. We're asked to calculate the volume of sodium hydroxide required to reach each equivalence point, 1 in part A and 2 in part B. Then we are asked to calculate the pH at each equivalence point. For part A, we have 42.2 milliliters of acetic acid at 0.0520 molar. So if we were to take the 0.0422 liters, which corresponds to 42.2 milliliters, multiply it by the concentration, we will get moles of acetic acid we are starting with. 1 mole of acetic acid reacts with 1 mole of base sodium hydroxide, because all acid-base titration reactions to reach an equivalence point, just one equivalence point, is a one-to-one stoichiometry. Once we have moles of base required, we can divide by the molarity of the base solution, 0.0372 molar, and we will get the liters of base required to neutralize this volume of acid. And we can multiply by 1,000 to get milliliters, 58.99 milliliters. Then we are asked to calculate the pH of the solution at the equivalence point. pH is always equal to the negative log of the hydronium concentration. So how are we going to calculate the hydronium concentration? Well, at the equivalence point, all of the acetic acid has turned into acetate. So we have the weak conjugate base of acetic acid. So we need to carry out a weak base Kb calculation in order to get the hydroxide concentration, which we can then use to get the hydronium concentration. So if then pH is equal to the negative log of the hydronium concentration, and we are calculating the hydroxide concentration first, then we need to divide the hydroxide concentration into Kw, 1.0 times 10 to the negative 14, to get our pH. So pH is equal to negative log of the hydronium concentration, which is the hydroxide concentration, divided into Kw. So how do we get the hydroxide concentration? Remember, if we have a weak base, the hydroxide concentration is equal to the square root of the Kb value. We don't have the Kb value for acetate, but we do have the Ka value. The Kb value will be the Ka value, 1.8 times 10 to the negative 5, divided into Kw. So the hydronium concentration is the square root of Kb multiplied by the weak base concentration. Well, all of the weak acid, acetic acid, has turned into the weak base. So if we take the volume times the molarity of acetic acid, we will get the moles of acetic acid we are starting with, which is now the moles of weak base acetate that we have. If we divide that by the new volume, then here what's in parentheses is the molarity of the weak base at the equivalence point. The new volume being the 42.2 milliliters, or 0.0422 liters, plus the equivalence point volume, 58.99 milliliters, or 0.05899 liters. So this is the weak base concentration, this is Kb. If we multiply them together and take the square root, this is hydroxide. We divide hydroxide into Kw. This gives us the hydronium concentration. We take the negative log of the hydronium concentration and we get pH, 8.54. Now for the next one, we have a diprotic acid, sulfurous acid. The first equivalence point will correspond to just the removal of one hydrogen. So if we start with the volume of sulfurous acid in liters, multiply it by the molarity of the sulfurous acid, we will get moles of sulfurous acid. 1 mole sulfurous acid, if only one hydrogen is coming off to reach the first equivalence point, corresponds to 1 mole of base sodium hydroxide. When we have mole sodium hydroxide, we'll divide by the molarity to get liters sodium hydroxide required to neutralize the first hydrogen of this volume of sulfurous acid, and then we can convert it to liters by multiplying by 1,000. So because we did a stoichiometry of 1 to 1, this is the volume that corresponds to just the first equivalence point. To calculate the pH at that first equivalence point, we actually have a amphoteric species, the HSO3-, that can behave as an acid and a base. So the pH is going to be equal to 1/2 pKa1 plus pKa2. pKa1 for sulfurous acid is, your values might differ, I'm using the values that I found, 1.3 times 10 to the negative 2, and then plus the pKa of the second hydrogen coming off of sulfurous acid, 6.0 times 10 to the negative 8, and we get a pH of 4.55 at the first equivalence point. This technique only works when we have an amphoteric species, such as what is created when one hydrogen comes off of a diprotic acid. Next, we're going to calculate the second equivalence point. The second equivalence point will correspond to double the first equivalence point, because the moles of sulfurous acid we start with will be equal to the moles of HSO3- at the first equivalence point, and then we would require the exact same amount of sodium hydroxide to convert that exact same number of now HSO3- into SO2-. So the second equivalence point would be reached at another 66.03 milliliters, or a total of 132.06 milliliters. To solve for the pH, we're going to do something very similar to what we did in this part of the problem. pH will be equal to the negative log of the hydronium concentration. The hydronium concentration will be equal to Kw divided by hydroxide. So how will we calculate the hydroxide concentration? Well, at the second equivalence point, all we have is SO3-, which is a weak base. To solve for the hydroxide concentration created by SO3-, we need to take the square root of Kb for SO3-. Kb for SO3-, is going to be Ka divided into Kw, and then multiply that by the concentration of SO3-. The concentration will be equal to the moles of sulfurous acid we started with. However many moles of sulfurous acid we had at the beginning, that's now how many moles of SO3-, we have. That can be calculated by taking the volume of sulfurous acid divided by, or multiplied by, the initial volume. Divide that now by the new volume. So this is moles SO3-, we have. Divide by the new volume, the 42.2 milliliters, or 0.0422 liters, plus the volume we just added, 132.06 milliliters, or 0.13206 liters, and we get a pH of 8.33. As we expect, we should see an increase in pH from the first equivalence point in comparison to the second equivalence point.